The Chinese remainder theorem guarantees that any system of congruences whose moduli are pairwise coprime has a solution, and that solution is unique mod the product of the moduli. Let's create an algorithm to find the solution. Remember, don't solve problems, create solutions. So let's consider a simple problem where we have two congruences. We find the greatest common divisor of our two moduli is 1, so the Chinese remainder theorem guarantees a solution exists. Now, previously we started with 0 congruent to 0 mod who cares what, then increased our value to solve each congruence separately. To avoid unsolving, we added multiples of the other congruence. So if we add 15, then our second congruence will remain unchanged, but our first one will be altered. So add 15 once, twice, 3 times, and we have a number that's congruent to 3 mod 14. But it's still congruent to 0 mod 15. Now, since 14 is congruent to 0 mod 14, we can add multiples of 14, and that won't change our first congruence. So we'll add, and add, and add, and we want to get down to 2 mod 15, but it seems like it's going to take a bit of effort. So always ask the question, what made this easy? Solving the first congruence was easy because 15 was congruent to 1 mod 14. So x congruent to 3 mod 14 has solution 3 times 15, or 45. Solving the second congruence was harder because 14 was congruent to 14 mod 15. So solving x congruent to 2 was harder. Now, note that we're actually trying to solve 45 plus 14k congruent to 2 mod 15. But since 45 is congruent to 0, this is just 14k congruent to 2 mod 15. And we can solve this by finding the multiplicative inverse of 14 mod 15. And it turns out the inverse is 14 itself, and so we find, which we can reduce, and consequently, 14 times 13 will be congruent to 2 mod 15. And so from our starting point, if we add 14 times 13, that's congruent to 0 mod 14, so that won't change the first congruence, but our second congruence will increase by 2, and we'll have a number that's congruent to 3 mod 14 and to 2 mod 15. We can reduce that. Since 14 times 15 is 210, we can reduce these values to, which is our least positive solution. So what if we have 3 congruences? So we can start by adding multiples of 6 times 7 until we solve the first congruence. This is the same as solving 42k congruent to 4 mod 5. To do that, we'll need the inverse of 42, well, that's really just 2 mod 5. That inverse is 3, so 42k congruent to 4 mod 5. I'll reduce that coefficient. I'll multiply by the inverse, and I get the solution k equals 2. And so we need to add 42 times 2, 84. Next, we need to add the multiples of 5 times 7, 35, until 84 plus 35k is congruent to 3 mod 6. Since 84 is congruent to 0 mod 6, this becomes 35k congruent to 3, and we need to find the inverse of 35, or 5 mod 6. The inverse is 5, and so we find, and so k is congruent to 3, and what we need to add is 35 times 3, 105. Finally, we want to add multiples of 5 times 6, 30, So that, and again, since 189 is congruent to 0 mod 7, this becomes, so we need to find the inverse of 30, which is 4, and so k is 5, and so we need to add 30 times 5, 150. And so our solution is 339. And we can add or subtract any multiple of the product of the moduli. So we subtract and get 129 as the least positive solution. So now let's turn this into an algorithm. So an algorithm is the automation of a problem-solving strategy. And when building an algorithm, it helps not to do the arithmetic. So here we found that our system of congruences had the solution, but in fact these numbers 2, 3, and 5 were found by multiplying where we see that each term is the product of the congruent, the product of the other moduli, and the inverse of the product with respect to the current modulus. And this suggests an algorithm for solving the Chinese remainder problem. So let's take a system of congruences. First, we'll find the inverse of 70, the product of the other moduli, mod 3, the first modulus. And we find that the inverse is 1, so our product of the other moduli, 70, times the inverse, 1, times a congruence, 1, 70, is part of the solution. Next, we'll find the inverse of 42, the product of the first and third moduli, mod 5, the second modulus. And we find that inverse is 3. So that product, 42, times the inverse, 3, times a congruent, 2, 252, is another part of the solution. Finally, we'll find the inverse of 15, the product of the first two moduli, mod 14, the third modulus. And we find that 15 times 1 is 1, so 15, the product of the other moduli, times 1, the inverse, times 3, the congruence, 45, is the third part of our solution. And so we add 70, we add 252, we add 45, and we get 367. And since the product of the moduli is 210, we can reduce mod 210 to get the least positive solution, 157.